right, so our first step is always to write out our given. In class, I don't write it out, but on a test or quiz, should you write it out? Yeah. Yes, absolutely. So here we have that ST, so you want to mark up your diagram, is congruent to SM. And each piece of given information that you go through, you're asking yourself, can I draw a conclusion from it? Can I draw any conclusions from ST congruent to SM? No. Then we have TP is congruent to MN. Again, no conclusion I can draw there. So now what is it that we want to prove? We want to prove that SP is congruent to SN. So this is going to be a two-step proof. We will be allowed to say that SP is congruent to SN. Who thinks they know the reason? Daniela. These aren't angles. Oh, I mean, segments. So the sum of congruent segments are congruent. So you would have to, we can't say the sum of congruent segments are congruent. You would have to, if you wanted to say the whole theorem, you would have to say if congruent segments are added to congruent segments, their sums are congruent. So if you wanted the theorem, you'd have to say that whole thing because what you said didn't translate exactly. Or we can just actually just say one word, which is addition. You got it.
So when do you know whether to write the theorem or whether to write addition and subtraction?
You always just write addition or subtraction. You never have to write out the theorem for addition or subtraction. A lot of students are choosing to do that because it just helps them remember it better. But you could always, if it falls under addition or subtraction, you could always just write addition or subtraction. All right, that's it. So it's just a two-step proof. So last class we learned addition and subtraction. Today, guess what we're learning? Multiplication and division. So let's just keep scrolling. I'm gonna tell you the foolproof methods of knowing when you'll use multiplication or division. Foolproof, yeah. So we are going to use multiplication or division if you see the double use of the words midpoint, trisect, or bisect. Any dividing word. What do I mean when I say double use of these words? What does that mean, double use? Yes. Simon?
Like if it says like there's like two midpoints.
Good. If it's written twice. So if midpoint is used twice, or trisect is used twice, or bisect is used twice. So right off the bat, when you're scanning the given information, if you see any of those dividing words, midpoint, trisect, bisect, if you see any of those dividing words written twice, you want to put in the back of your head, okay, I'll most likely be using multiplication or division in this proof. Right. Generally speaking, let's just stick with whole numbers, not integers. When you're multiplying, are you making things bigger or making things smaller? Bigger. Generally speaking, when you're dividing, let's just stick with, well, I guess we could get fractions. But generally speaking, if you're dividing, are you making things bigger or smaller? Smaller, exactly. So step number one, look for a double use of one of those dividing words. And then decide, are we going bigger or are we going smaller? Let's do a proof. All right, given MP is congruent to NS. So MP is congruent to NS. Now I'm scanning real quick. What do you think should be jumping out at me since I'm scanning my given? Sam. Good. We have the double use of the word midpoint. Anytime you have double use of any of those dividing words, in the back of your head, you should be thinking, okay, I'm going to use multiplication or division in this proof. Now, something else to tell you. If you're going to use multiplication or division, you do not have to go through the function of the midpoint. What do I mean by that? You know how I always say read the given, make a conclusion? So if we're reading the given and it says O is the midpoint, wouldn't we say MO is congruent to OP, definition of midpoint? But since we're going to use multiplication or division, we do not need to go through the function of that dividing word. I'm going to say it one more time. If we're using multiplication or division, you do not need to go through the function of the dividing word, meaning I don't need to say MO is congruent to OP, definition of midpoint. I do not need to say NR is congruent to RS, definition of midpoint. That's only if you're using multiplication or division.
If we accidentally did it on a test, would you mark it wrong?
I'm sorry, say it one more time.
If we accidentally did that.
Wrote out like no, I wouldn't mark it wrong. It's just extra steps that you wouldn't need. All right, so now it's saying, I know I'm using multiplication or division. Since I know there's the double use of the word midpoint, that I'm using multiplication or division, do I need to go through the function of a midpoint? No. So let's look at what we want to prove. We want to prove that MO is congruent to NR. Just to show you, the definition of midpoint, would the definition of the midpoint make MO and NR congruent?
No.
No. What would the definition of the midpoint make? MO and OP congruent. So this is not definition of midpoint, right? They're in two different segments. So now, the way I'm looking at this, the whole segments are congruent, right? What does a midpoint do? Doesn't it cut something in half?
Yes.
So if the whole segments are congruent, are their half segments also congruent?
Yes.
So I was giving you the big segments congruent, and I want you to prove the half segments congruent. So we're going big to small. So I gave you big, we're going smaller. Which one is that, multiplication or division? Division. So we're going to go in and we're going to say MO is congruent to NR division. Michael? So how would you make subtraction work here? So let's go through what you're saying. So then the way you're saying is, let's go through the definition of midpoint, right? So we would say that MO is congruent to OP. Do you agree with that? And then we'd say NR is congruent to RS. Look at my markings. They're different. So there's no way to connect MO and NR, because the definition of midpoint just says that these two are congruent. The definition of midpoint just says that these two are congruent. So there's no congruent numbers to subtract away. Does that make sense? So the division is saying, well, the whole segments are congruent, and I'm dividing in half. So if the whole segments are congruent, then if I divide by 2, their halves will also be congruent. Does that make sense? Okay. All right, let's look at example 2. So here we have angle TRY. So this whole angle is congruent to angle ABE, this whole big angle. And then I'm scanning real quick. I scan real quick, and what should I notice right away? It says trisect twice. If it says trisect twice, what should that tell me in the back of my head? Multiplication or division. Because I'm using multiplication or division, do I need to go through the function of a trisector?
No.
No, so I do not need to write def of trisector. If I were not using multiplication or division, would I need to go through the function of a trisector?
Yes.
Absolutely. So let's look. Oh, I forgot my little angle symbol here. There should be an angle symbol there. All right, we want to prove that angle TRW, that's this angle right here, is congruent to angle CBD, which is this angle right here. Do they look like they're congruent?
No.
No, does that matter?
No.
No, nothing is drawn to scale. Exactly. So now we know we're using multiplication or division. Do we agree when you bisect, you divide by 2, or midpoint, you divide by 2? When you trisect, you divide by 3. So if the whole angles are congruent and we divide by 3, would their thirds also be congruent? Yeah, so we have the whole angles congruent and we're proving just a third of them congruent. Maya?
Wouldn't they like automatically all the angles be congruent because they're being trisected?
It would only work if if the original big angles were congruent. So because the big angles, like let's say the big angles weren't congruent. So let's say this angle was, I don't know, 90, and this angle was 60. So then this trisect would be 30, 30, 30, and this trisect would be 20, 20, 20. So for this one, because I told you that the big angles were congruent, so this one is congruent to this one, so now I'm starting off by stating, okay, well, these both have to be the same, so they both have to be 60, or whatever it is. And then when you trisect, what do? You divide by 3. So this would be 20, 20, 20, and this would be 20, 20, 20. Oh, you're saying, why can't we just say def of trisect? Is that what you're asking? Okay, let me show you why. Because the definition of trisect doesn't relate one angle to the other angle. So the definition of trisect would just say this angle is congruent to this angle, congruent to this angle. And on the other side, when it said trisect, it would say this angle is congruent to this angle, congruent to this angle. The definition of trisect doesn't relate the two separate angles. Does that make sense? So I wasn't asking you to prove like this and this. If I was saying, okay, prove these two angles congruent in the same angle, then it would just be def of trisect. But I'm saying prove one angle from this and one angle from that to be congruent. So then the def of trisector doesn't relate those.
So when there's like two angles, like you don't really have to. When there's like two angles on like different ones, you don't have to do def and trisect.
Well, it depends on what you want to prove. Sometimes you would have to. So sometimes it's multiple steps. Sometimes you're going to have to do the definition of trisect and then do something else after that. It just depends on what we need from it. Livy?
I'm just like if we did def of trisect on a test, it would be wrong because like since the angles are congruent, like and they're both trisected, isn't that just?
But so you have to go by what it actually means. So the definition of trisector is, you know, two lines, right, or segments that split an angle into 3 congruent angles. So by your definition of trisector, you would say angle 1's congruent to angle 2, congruent to angle 3, definition of trisector. And then on the other side, we'd have 4, 5, 6. But then now this definition of trisector would just say angle 4 is congruent to angle 5, congruent to angle 6. The definition of trisector doesn't relate the two different angles together. You understand? So definition of trisector wouldn't help us out here. But division does help us out because division's not saying, okay, the 3 angles are congruent. The division is saying, well, if the whole angles are congruent and then I divide by 3, aren't their thirds also congruent? That's what the division is saying. So we're going to go ahead and we want to say angle TRW is congruent to angle CBD, division. Michael?
Is there a long version of the reason that
Oh, yes. So the division theorems are up here. So if segments, for multiplication, it's if segments or angles are congruent, they're like multiples are congruent. And if segments or angles are congruent, they're like divisions are congruent. We good? All right, let's look at this next one.
Let me just like multiplication or division property and I'll be fine.
Yep, you'll be fine.
Okay.
So here we're having that MK, so I'm marking it, is congruent to FG. And then it says KG bisects MJ and FH. Technically speaking, how many times has the word bisect been written down? Once, right? Technically, it's just written down once. But how many times is it implied?
Twice.
Twice. Exactly. So even though bisect has only been written down one time, it's implied twice because it says and. So we could have split this into two statements. We could have written KG bisects MJ and then underneath of it, KG bisects FH. So do you think this falls under multiplication or division?
Yes.
Yes, absolutely. All right, what is it that we want to prove? We want to prove that MJ is congruent to FH. So we want to prove this whole top segment is congruent to this whole bottom segment. Now, a bisector, doesn't it cut something in half? All right, so right now I'm showing you that the half segments are congruent. If the half segments are congruent, are the whole segments also congruent? Yeah, you just multiply by 2, right? So what do you think this is? I'm giving you small, we're proving bigger. Multiplication. So MJ is congruent to FH multiplication. Can I keep going? Are we ready to try one that's not 2 steps? We ready for this? Let's do this. All right. So remember what I tell you to do. Go through, try to make conclusions if you can. Angle NOP, so that's this big angle, is congruent to angle RPO, which is this big angle. Then I'm scanning, and what should stick out at me? It says bisect twice. Because it says bisect twice, do I need to go through the function of a bisector? No, I do not need to go through the function of the bisector. And I also know that I'll be using multiplication or division. All right, because I know I'm going to be using multiplication or division, and what are we bisecting? Aren't we bisecting the big angle P, and aren't we bisecting the big angle O?
Yeah.
Let's use multiplication or division. So if the whole angles are congruent, am I going to be multiplying? Could I multiply to get any bigger?
No.
No, the whole angles are already congruent. I can't go any bigger. Since the whole angles are already congruent, the only way I can go is smaller. So, do we see angles in here?
Yes.
Yeah, which angles, if you were to take a guess, would you say are congruent? Michael? S, say it one more time. SOP, TPO. So let's call them angle 2 and 4. Those two? All right, is only 2 and 4 congruent?
No.
What else are congruent?
1 and 3.
Are all 4 of them congruent?
Yes.
Yeah, should we be safe and just say all 4 of them are congruent? Yeah, let's go ahead and say all 4 of them are congruent. So I'm going to say angle 1's congruent to angle 2, which is congruent to angle 3, which is congruent to angle 4. And what was this? If the whole angles are congruent and then we divided them by 2, their halves are also congruent. Big to small, what is that? Division. All right, let's keep going. Now we're saying that angle NSO, should I put an angle 5 right here, or do you guys want to just name it NSO? NSO, okay, so let's put a star in NSO, is a complement to angle 1. So let's put a star by angle 1. Then it says angle RTP, let's put a dot, angle RTP, let's put a dot here, is a complement to angle 3. Let's put a dot by angle 3. Now we want to prove that angle NSO, this star, is congruent to angle RTP, this one. Oh, what did I forget to do? When we said all 4 angles were congruent, we forgot to mark them. 1, 2, 3, 4. All right. Well, look at what's happening here. Star, star, dot, dot, congruent, right? Angle 1's congruent to angle 3 by division. And then 1 is a complement to this star, and 3 is a complement to this dot. Julia. Excellent. Complements of congruent angles are congruent. So now we can go ahead and we can say angle NSO is congruent to angle RTP. Comps of congruent angles are congruent. It looked a lot more intimidating than it really was, right? No, it was intimidating. Anybody still copying this down? We're good? Okay. All right, you have one to try on your own, and then we're done for the day. Try this on.
It's not that much. It's only 2 new things.
Yeah, wasn't too bad today.
Homework is also
Yeah,
a
no.
nice question.
I try not to give too much homework.
Pretty.
We could actually take off number 16 in the homework.
Really?
Yeah,
Okay. I'll write that down.
I'll put it on Classroom.